This first unit of data management is all about probability, just sort of an introduction to it. So we've already looked at experimental and theoretical probabilities, which we definitely need to know. But there's a couple of other really key ideas that are going to carry through with probability. So again, this unit is about learning some tools that we can carry forward into other units of the course. And one of those tools is mutually exclusive, the idea of mutual exclusivity. So we're going to look at mutually exclusive events and non-mutually exclusive events and try to be clear on when we're dealing with which kind of event. So when calculating the probability of either one event happening or another happening, it's important to carefully count the outcomes. It's always important to carefully count the outcomes. So it doesn't, that's not specific, but it is definitely always important to count outcomes, because probability is based on outcomes. Outcomes, successful outcomes, total outcomes, we need to be able to count those. So when two events have completely different characteristics, they're said to have mutually exclusive events, or they're said to be mutually exclusive events. Completely different characteristics. In other words, they don't overlap. So one event can happen or the other, but not both. And we can see that on a Venn diagram. Here's we talked about Venn diagram a couple of lessons ago. Here's another Venn diagram. So the whole big rectangle is the sample space, which I will designate as S. I'll just put that beside it. And then if we got a couple of events, let's say that I'm talking about a deck of cards. And you can see a deck of cards down here, in fact. So here's some kings. Here's some aces down at this end. Okay, so there's some kings and some aces. So if I let event A be drawing a king, then in sample space A, there are 4 kings. There's king of hearts, king of clubs, king of diamonds, and king of spades. That's event A. Event B would be drawing an ace. And that, there's no overlap, right? I can put my 4 aces. I also have 4 aces, just like I have 4 kings. So ace of hearts, ace of clubs, and so on. Okay? It's one or the other. And by the way, all the rest of the cards, those other 48 cards, they would all be represented by this area outside both these circles if I was to fill them in. So that's what the rest of the sample space is. So things don't have to be in either one of the circles. But anyway, as far as the kings and the aces go, we have these 2 separate circles which don't touch each other. And they don't touch each other because if something's a king, it's not also an ace. So those are what we would call mutually exclusive events. So the additive principle, rule of sum for mutually exclusive events, says that the probability of either of 2 mutually exclusive events, A or B, is adding the 2 probabilities together. All right? So this is an important formula. And it's a simple one. So the probability of A happening, of either A or B happening, would be the same as the probability of adding the 2 together. So if I want to just extend the example I did up above, probability of A or B here, the probability of A getting a king is 4 kings over 52 cards in a deck. The probability of getting an ace is 4 aces out of 52 cards in a deck. So the probability of getting a king or an ace, if I just said, all right, here's a deck of cards, and what's the probability if you pull a card out that's either a king or an ace, it doesn't matter which one, well, then it's 8 over 52, which we would reduce, of course. That would be 2 over 13, but that's beside the point. The main point I'm putting right now, or making right now, is that we add them together. So let's take a look at a couple other examples farther down. What's the probability of drawing a red face card or a black ace? Well, let's look at a Venn diagram again. Red face cards are mutually exclusive from black aces. In fact, any red card is mutually exclusive from any black card. If A is my red face, then, in case you're not familiar with decks of cards, the hearts and the diamonds are the red ones. I'll just throw some red highlighter on there, and the other 2 rows are black cards. As you can see, there's 6 face cards. Those are the ones with the pictures on them. So we've got the Jack of Diamonds, King of Diamonds, Queen of Diamonds, Jack of Hearts, Queen of Hearts, and King of Hearts. There's 6 red face cards. And if B is a black ace, there's the ace of clubs. And that was supposed to be a club. Terrible drawing. Let's try that again. And there's the ace of spades. So there's 2 of those. Because they are non-mutually exclusive, we'll be able to use the rule of sum, the additive principle. The sample space, by the way, is the 52 cards in a deck. So n of s equals 52 cards in the deck. So the probability of A or B is equal to the probability of A plus the probability of B, which is 6 over 52 plus 2 over 52, which equals 8 over 52, which again reduces to 2 over 13. So those are mutually exclusive events. So everything, the ones that we've looked at so far are mutually exclusive, and from a Venn diagram, they're very easy to recognize. The circles do not overlap. However, in some situations, it is possible for different events to occur simultaneously at the same time. When the 2 events have some characteristics that are the same, that's mutually exclusive. Sorry. No, I said the exact wrong thing. That's non-mutually exclusive. So the Venn diagram would look like this one here on the right. We'd have this event A and event B that are non-mutually exclusive, and we've got this overlap here. And overlaps make things trickier because we have this tendency to double count things in the overlap. And so we have to watch out for that. So I'm going to put a caution here. It's supposed to be an arrow. Don't overcount the overlap. So, for example, a standard deck of cards again. How many ways could you draw a diamond or a face card? Use a Venn diagram to illustrate the favorable outcomes. Alright, well, as far as, let's draw our Venn diagram actually. There is going to be some overlap, so I'm going to make sure I account for that. Alright, so if I let event A be drawing a diamond, then here in my A circle, we're going to have all the diamonds. And if I let event B be a face card, then all the face cards would go in circle B. The thing is, there's some diamonds that are face cards. In particular, we've got the Jack of Diamonds, the Queen of Diamonds, and the King of Diamonds. So notice how that's inside the diamond circle, but it's also inside the face card circle. Now there's other things inside the diamond circle that aren't in the face card circle. There's the Ace of Diamonds, there's the Two of Diamonds, the Three of Diamonds, and so on. So these are all diamonds, but they're not face cards. There's also a lot of face cards that aren't diamonds in this B circle. There's the Jack of Clubs. There's the Queen of Clubs. I'm getting worse at drawing clubs. Oh well, I won't bother trying to take time to fix it. We've got the Jack of Hearts. Those are a little easier to draw. Although I'm still not doing a great job, am I? And finally, we got the Jack, Queen, and King of Spades. Somehow those ones seem easiest for me, except for that little blip at the end. Anyway, there's a nice sketch. How many diamonds are there altogether? Well, N of A is all the diamonds, and if you count up all the things in this circle here, you'll find 13 cards. And N of B is all the face cards. And everything, if you count up all the cards in this circle, there's 12. But if we want the overlap, N of A and B, that's just what I've highlighted in yellow. Those are the 3 cards. So if I want to know the total number of diamonds or face cards, then I can use the counting strategy known as the principle of inclusion and exclusion, using the additive principle. And it's N of A or B equals the N of A plus N of B minus N of A and B. So notice how these are N's here. So it's not probability, it's just adding up the number of them. We're going to see a probability thing associated with this in a minute, but we're using N just for the number. So I want to know the total number of A or B, in this case, total number of diamonds or face cards. It's the total number of diamonds plus the total number of face cards minus the overlap, right? Because remember what I said about caution, don't count the overlap? What happens if we just add them both together is we end up counting those 3 diamonds, the Jack of Diamonds, Queen of Diamonds, and King of Diamonds. We end up counting those twice. That's why we subtract here, because that'll take away that double counting. So for this example, what we have is N of A or B equals 13 plus 12 minus 3. And so it turns out that there's actually 22 cards that we could pull that are either diamond or face or both. In a room with 30 students, 10 play basketball, 15 play volleyball, okay? 30 students may be important as well. If 7 students play both sports, how many play basketball or volleyball? Okay, so it gets a bit confusing. So we need to start labeling things a bit. So let's let event A be basketball, because we know that 10 play basketball. So N of A equals 10. And if we let B be volleyball, let's just do it over here actually. Volleyball, is there an E in there? I think there is, it's right, yes, volleyball. So N of B was 15. And students who play both would be N of A and B. So that would be the 7 students who play both. So the students who play basketball or volleyball, when they say play basketball or volleyball, they basically mean play basketball or volleyball or both. So we can add them together. We want to find N of A or B, but they're not mutually exclusive, right? Because some of the basketball players play volleyball, some of the volleyball players play basketball. They overlap. So it's going to be the 10 plus the 15 minus the 7. 10, 15, 7. Let's highlight a bit. So that gives me 18 players who play basketball or volleyball or both. To extend this idea of the principle of inclusion and exclusion for counting, we can also use it, just a pretty much identical formula for doing probabilities. So to calculate the probability of either non-mutually exclusive events A or B occurring, we use the additive principle for non-mutually exclusive events. So compare this formula here to the one just above it here, and you'll see that they are identical except for the fact that we've got N, 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 N compared to P, 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 P. So the one at the top is counting up the number of whatever, whereas P is calculating the probabilities. So we can add the probabilities together and subtract the probability of overlap using the exact same formula. Now there's one thing that I just want to add on here, because sometimes we might see it. So I'm just going to add quickly one more formula here at the bottom. Draw a line. And what if we have 3 groups of non-mutually exclusive events? So here's a diagram. And so for 3 events, no, I didn't want a square, I wanted a circle. Picked the wrong one. One more try. There we go. There, that's nice. Let's call them A, B, and C. What you'll notice is there's a lot of overlap going on, or at least there could be. We've got A overlapping B, we've got B overlapping C, we've got C overlapping A, but we could even have A and B and C all overlapping, as I've shown here with the green. Is there a version of the additive principle for non-mutually exclusive events for that? And the answer is yes. Whether we use N or P, I'll write it in terms of N, but P would be true as well. If I want to find the number of A or B or C, that's going to be equal to the number of A plus the number of B plus the number of C. And then we've got that overlap of A and B, which we don't want to double count, so we're going to subtract the number of A and B. And we also want to subtract the number of B and C. And we want to subtract the number of A and C, because that's also an overlap. However, we've subtracted so many overlaps that now we've subtracted this green center one too many times. We've actually taken away too much. And so that green center one has been subtracted individually by these combinations so many times that we actually need to add it back in. So we need to add back in the overlap of A and B and C. So let's just put some colors here. So these are the ones we're subtracting, the ones that I've highlighted in yellow, but that also includes that middle thing. And then we're going to add just the middle back in one more time. So if I had specific numbers, then I could always, then it'd be clear. And you might see an example like that in the near future. But for now, just keep this formula in the back of your mind.